Okay, guys, so in class today, several of you wanted me to do numbers 13, 14, and 15 from the homework. So I'm going to work through each of these problems with you. Hopefully this will help. So let's just take a look at number 13. It tells us in the problem that iron is biologically important in the transport of oxygen by the red blood cells from the lungs to various organs in the body. And then here's where it starts giving us some information. So I'm going to jot down what I call my knowns and then my unknowns. So it says in the blood of an adult human, there are approximately 2.60 times 10 to the 13th red blood cells with a total of 2.90 grams of iron. Now let's know on average how many iron atoms are present in each red blood cell. And they give us the molar mass of iron. So I'm just going to make a table here with my knowns and my unknown. And remember I said in class today, focus on your units. So what they're asking you to find here is they want to know how many atoms of iron are per red blood cell or in each red blood cell. So atoms per red blood cell. So that's how I'm going to write that unit. And then something else they told us was that, and we can use this as a conversion factor, that there are approximately 2.60 times 10 to the 13th red blood cells, and it said with a total of 2.90 grams of iron. So what that means is equivalent to 2.90 grams of iron. So we can make a conversion factor out of this. We also know, since we're trying to get to atoms, we're going to have to use Avogadro's number, which is 6 times 10 to the 23rd, in this case, atoms, equal to 1 mole of any substance. And then, of course, they gave us the molar mass of iron was 55.85 grams per mole. So these are all of our known informations. So I'm going to start this as a dimensional analysis problem, and I'm going to start off using this as my given, but I'm going to make it as a like a ratio because they're giving us the ratio here. And since I need atoms as my final unit, and I need red blood cells on bottom as my denominator, I'm going to write this so the red blood cells are on bottom. So what I mean by that is I'm going to write as my given 2.90 grams of iron, and underneath it, because it says it's equal to it, 2.60 times 10 to the 13th RBC, red blood cells. So they tell us 2.90 grams of iron are contain approximately 2.60 times 10 to the 13th red blood cells. And over here, I'm going to write down the unit I'm looking for, which I need atoms of iron on top, and that'll be per red blood cell. So what I want you to notice is, see how red blood cells is on the denominator in this part, and it's in the denominator here. So that means I need to leave the red blood cells alone, okay? That's going to be in my denominator. What I've got to work on is getting grams converted to atoms. So this is where the molar mass comes in. We're going to use the molar mass, 55.85 grams of iron equals 1 mole of iron. Okay, so we're going to divide by the molar mass, and then that's going to give us moles per red blood cell. Well, we don't want moles as our numerator, we want atoms. So this is where Avogadro's number comes in. So according to Avogadro's number, we know there are 6 times 10 to the 23rd atoms in 1 mole of any substance. Notice this lets your moles cancel out, and that's kind of hard to see, so let me mark that out with a different color. So grams cancel with grams, moles cancel with moles, and you have atoms. So notice your unit is going to be atoms in your numerator and red blood cells in the denominator, and that's what you want, atoms per red blood cell. So now you're able to multiply 2.90 times Avogadro's number, and then divide by the 2.60 times 10 to the 13th, and then divide by the 55.85. Okay? And you're going to round that so that it has 3 significant figures. And that's going to give you 1.20 times 10 to the 9th. That's your answer. All right, number 14. 14 says we have an unknown oxide, metal oxide, and so it gives you this formula, M2O3. So I'm going to write that down, M2O3. These are things we know. And it tells us that it's 68.4% of the metal by mass. You think about percent composition. And it wants you to find the unknown is the atomic mass of the metal. So that's going to be the grams per mole, the molar mass of the metal. All right. All right, now remember, in a compound, your percents of your elements have to add up to 100. So the easiest way to approach this problem is to approach it from the oxygen standpoint. At least that's what I did. That's going to make it easier to solve, but you could approach it from the percent of the metal. If we know that 68.4 plus the percent of the oxygen has to equal to 100, if you say 100 minus 68.4, that's going to give us the percent of oxygen. And that's what I did to start my problem off. I went ahead and subtracted my percent oxygen. So the percent oxygen is 31.6%. And again, these two have to add together to give you 100. So if you think in terms of percent composition, percent oxygen will be equal to 48.00, because there's 3 oxygens in the compound, so 3 times 16 would give you 48. And then you would divide by the total molar mass. So if we want to make a molar mass of this, even though we don't know M's mass, that's what we're trying to find, we know that it's going to be equal to 2 times whatever M is, plus 48, because 48, there's 3 oxygens here. And then, of course, times 100 to make it the percent. So what you're going to do at this point here is you're going to plug in your percent oxygen, because we know that. So you're going to plug in 31.6% equals 48, and I'm not going to worry about sig figs right now. I'm just going to write it in as more of an algebra problem. So 48 divided by 2m plus 48 times 100. And from here, you should be able to solve, because once you solve for m, that will be your answer. Let me just talk you through it. You would divide both sides by 100. That would give you 0.316 equals 48 over 2m plus 48. And so now you're going to cross multiply and distribute. So you're going to say 0.316 times 2m plus 48 equals 48. Okay, and I'm not going to finish it out completely here, but I'll talk you through. You distribute that in, and then you're going to collect your like terms and you will solve. Okay, and that's going to end up giving you, for the m when you're done, you end up getting 51.9 grams per mole, because you're looking for the atomic mass of the metal. Okay, that's number 14. I'll let y'all do the algebra on that one. That should be enough information there. All right, the last one, number 15. It says, what's the molar mass of a compound in which 1.0 grams represents 5.9 times 10 to the negative 2 moles? Now, if you're looking for molar mass, remember the units for molar mass are the grams per mole. That's the unit you've got to get. Well, they gave you the grams, 1.0 grams. They also gave you the moles, 5.9 times 10 to the negative 2 moles. So if you look, your unit, grams over moles, all you got to do is divide here, guys. 1.0 divided by 5.9 times 10 to the negative 2, and that's going to give you 16.949, which would round to 17 grams per mole. Okay, I hope that helps.